Hello everyone, today we're getting deeper into linear algebra. So today, the thing we're going to talk about is matrix. So actually, what is a matrix? So one of the most easiest way to understand matrix is that understand it as a collection of coefficients in the system of linear equations. So as you can see here is the system of linear equations and it is not complex at all. It's just two linear equations here. Negative x1 plus 2x2 is equal to the constant 1, and x1 plus x2 equal to constant 2. So basically, here we can write a matrix for this system of equation as such. Negative 1, 2, 1, 1. And we can further defactorize it as two subvectors, and which is negative 1, 1. And v2 is equal to 2, 1. So far, it has been really easy. However, it definitely has a deeper meaning than just to represent the system of linear equations. So basically, how you can understand it here is that the space and the Euclidean space, since we have only two variables here, x1 and x2, which means we are doing all of our calculation in a two-dimensional Euclidean space. So basically, there's just one x-axis and one y-axis, and all of the computation is done on this surface. So basically, we can do here is that originally this space, if you draw the grid line here, is going to be like this, just normal grid line. I mean, one is one, and the space for each grid here is just one, unit one. However, if you apply this system of linear equation to this surface, it's going to stretch the surface, okay? So basically, V1 is going to take control of that actually it doesn't matter here. Let's say x1 stretch the x-axis, or y1, the first vector stretch the x-axis, and the second vector stretch the y-axis. As you can see, okay, let's draw it larger here. This is how the coordinates are transformed after the that A. This is just a notation for the matrix A. So it's gonna be like this. So V1, okay, this is negative 1, 1. Oh shoot, wait a minute. Uh-oh. Okay, yeah, matrix A. So this is how we represent the first matrix. It's gonna be the first matrix. Okay, V1 here. And the V2. Okay, so how do we represent the V2? It's gonna be like this. This is 2, this is 1, this is 1, this is negative 1. Then you connect the dots. Oh no, you just, okay, extend these two lines, extend these two vectors. So it's gonna be like this. Uh-oh, it's gonna be like this. After stretching it, as you can see, the grid no longer has area of 1, it no longer has. So the length of this vector is uh, 2, the root of 2. And the length of this vector is going to be root 5. So basically, the length is going to be root 10 over 2. This is going to be the space of one grid here. Extend the line here so you can see it better. So basically, a matrix is definitely more than the representation of a system of linear equations. It is also a transformation of the coordinates. So this is just on the 2D surfaces, okay, 2D surfaces. We can extend the same rule, the same operation to a 3D space. You're gonna stretch the unit area, the unit volume of each grid in the 3D space. But the math is gonna get really complicated here. However, if you just do it on the 2D surface, it's more intuitive and it's easier for you to understand. Okay, so now we can do a little practice here, okay? Now let's look at this question. A is as such. This is a matrix A. 2, 4, 2 through 4, -1, 5, -3, 6, -2, 8. So here is the matrix. And here is the weight. Okay, this is another like professional term in linear algebra, is that the collection of all of the variable in your function. And now here is going to be x is equal to x1, x2, x3. Since we have 3 variables here, this is the whole calculation should be done in a 3D space. So this is another very fundamental theorem in linear algebra, is that the matrix formula AX equal to B. The A here is matrix, and X here are the weights. Okay, the weights. Now the fancy term for all of the variables. And B here, it's just there. It's a B. Yeah, it is a B. And so how do we write this in such a form? A times X. Okay, so when you look at the matrix, first row, second row, third row, each row correspond to a equation. Each row correspond to an equation to the collection of the linear system. So as for the first row, we got 2, 3, 4 correspond to these 3 variables, x1, x2, x3. So when we actually multiply the weights and the matrix, the system is going to be like this: 2x1 plus 3x2 plus 4x3 equal to C1. Okay, C1. And negative x2 plus 5, oh shoot, 1 plus negative 3 times x3, okay, equals to C2. And 6x1 minus 2x2 and plus 8 x3, it's C3. So basically, this is how we actually multiply a matrix and weights. This is the collection of the linear system. So basically, that's it. That's all we have for today. So a brief introduction to the matrix formula, which is really important, and just took a pretty shallow insight into what is a matrix, the meaning and the essence of a matrix. Transformation is really important, which is going to come up pretty frequently in the later videos. There are going to be a lot about transformation, and there are many applications you can do with it. It's interesting. See ya.